with a lot of people moving towards 25 gig, 40 gig, and there's a lot of people looking at 100 gig at the moment into the servers.
Right.
That's not a linear increase. And if you match that up with the fact that there's no more free cycles from a CPU perspective, we need to start looking at what do we do to help with the networking workload.
We're here at Netronome. I'm talking with Niel. And Niel, I know you guys for things like coprocessors and the network processors and the smart NICs. So why don't we start by talking about coprocessors? What's going on in that world?
There's a whole big change that's occurring in the call it the processor industry today, specifically around silicon. Firstly, with the huge growth in the cloud, of course, we're seeing more of the general purpose usage of servers for lots of tasks in the cloud and so on. And that's been sort of an interesting evolution where we now see new entrants actually entering against sort of the hegemony that Intel has had in that market. Fundamentally, because of the demise of Moore's Law, from a silicon perspective, there's no more free CPU cycles around.
And we can't afford Moore's Law anymore.
We can't afford it. The way to keep that sort of scaling going is to use what is called application-specific processors or domain-specific processors. A few years ago in the cloud, a typical server would be connected at 1 gigabit per second. Networking wasn't really a big problem at those speeds, in virtualization and virtual switching and so on. Now what we see is that is scaled to 10 gigs, so the dominant interface now is 10 gig into the servers, with a lot of people moving towards 25 gig, 40 gig, and there's a lot of people looking at 100 gig at the moment into the servers.
Right.
That's not a linear increase. And if you match that up with the fact that there's no more free cycles from a CPU perspective, we need to start looking at what do we do to help with the networking workloads.
And I suppose doing something like putting a networking ASIC inside the server, like you would with a router or a switch, is out of the question.
When the network speeds increase like that, it brings us to problems in terms of security and visibility. Because we typically want to be able to inspect. If you have a 10x increase, but you're not getting any CPU increases for that, you have a problem. So what that has caused is the opening for smart NICs, as they're called in the industry, and obviously that's a segment where we play.
Security hasn't come up very much. Now it's the topic everyone wants to get in on, so you must have a security angle, right?
Yeah, so historically, actually, most of our revenues have come out of the security application of smart NICs.
Oh, really?
Just for what it's worth.
Okay, I did not know that.
But once again, we're seeing changes in the industry where, due to the sheer bandwidth and say some of the hyperscale guys, and we'll see that in anybody that's network focused, such as some of the carriers with NFV, even large enterprises, that there's two effects here. One is that the security perimeter has disappeared. So you can't block at your edge anymore. Yes, you still put boxes there and so on, you have to put them there, but you also need to distribute the security right down literally to your servers, to your wireless access points, and essentially we call it sort of the pushing towards the edge. Something which has had been established by the hyperscale players, where just the sheer bandwidth that they need to look at, and especially where it's infrastructure as a service. In other words, you're selling VMs to people anywhere in your data center, you need to make sure everything's secured. So there's two pieces there. There's both the piece around visibility, there's pieces around the ability to do that at speeds while the speeds are increasing at this level. It's basically the offloading function and being able to do that at scale for web services and a variety of other services, which is becoming interesting. So that ups the use of encryption accelerators as part of your data flow through the NICs.
So let's talk a little bit about networking itself and the Linux kernel. I'm familiar with DPDK, where the whole idea is to take networking out of the kernel for performance reasons. But you're telling me there's a kind of mirror image effort going on. What's that about?
Yeah, so it's a mouthful. It's called XDP eBPF,
Okay.
which allows you to do much higher performance networking in the kernel than what historically had been possible due to certain internal structures and so on.
Okay.
And that allows you to write programs within the kernel without having to necessarily patch the kernels and so on.
Okay.
So it's easy to get new functionality.
What is the interest there? I mean, we already have DPDK. Why bother putting things back into the kernel?
So a number of the hyperscale players and some of the web scale companies do typically do denial of service detection, do load balancing within their environments with just standard Linux servers, have either deployed it or are deploying it already because it's a standard upstreamed into the Linux kernel now as mechanisms to achieve these much higher performance goals without going into user space because of the fact that historically they use a lot of kernel services.
Okay, so they haven't even been using DPDK then, have they?
They typically have not used DPDK.
Oh,
yes.
Interesting. What does this mean for you guys?
We handle DPDK without obviously any problems, and we fully support many of the DPDK extensions. We offload OVS as an example through mechanisms which is based on the traffic control elements within the kernel, TC, which is a supported way and is being upstreamed at the moment within the OVS community. So we can play all of the different games, but the interesting thing is this whole notion of the kernel and offloading the kernel is very efficient and then keeps you compatible with all of the kernel services whilst achieving more than DPDK performance levels, because obviously we're faster than using DPDK without acceleration as well.
Okay. Very interesting. Well, thank you, Niel. It's great talking to you.
Excellent.